Non-negative unimodal factorization. So let's see what is it, why, how to solve it, and what is known about it. You probably have already seen this problem many times, that is minimize ax minus b subject to a constraint C or regularizer C. And the commonly seen regularizer are LP norm, sparsity norm, total variation, smoothness, blah blah blah. In this talk, we are going to talk about a very specific structure called unimodal structure, NU. So what is nu? This is the definition. You have a vector A. A1 is smaller than A2, which is smaller than A3, and so on, up to AP. That means you're having an increasing head of the vector. And then after AP, you're having a decreasing tail. So this is called NU. Looking at this, the first thing in your mind may be a Gaussian wave is NU. Yes, that's a typical NU vector, but NU is more than that. These three vectors are all NU. They all fulfill the definition of NU. Now we characterize the NU set. A vector X is NU if and only if X is inside the NU set of vectors with the P known. In general, P is unknown, so I define it like this. NU set, this U and U plus have some special property. First of all, this set is convex. For the NU set that P is unknown, it's non-convex. For example, we have two NU vectors here. These two vectors are NU, but the union, not NU. For this union, if these two vectors, their tips are closer together such that the changing point, the P, is a consecutive number, that is, this union set, in fact, this set is convex. And we can characterize the NU membership, that is, a vector X is NU if and only if this X is inside this union for a P. This membership characterization actually can be expressed by a matrix vector product. First, by definition of the NU, we can write down this system of inequality. And this can be expressed by using a matrix UP, which has this structure. It's built on a first order difference operator D. What we have seen is NU. Then what is NUMF? It's basically non-negative matrix factorization, MMF, with NU constraint. So what is NMF? This is NMF. You are given a matrix M, you want to factorize it as W times H, such that all the elements in W and all the elements in H are non-negative. So what is NUMF? You solve this problem, minimizing this distance subject to H is elementarized non-negative, and then the columns of W, denoted by Wj, is NU. This is just a normalization constraint for W. And if we apply the NU characterization, this is translated to this inequality, then we introduce integer unknowns. This is the NUMF problem. So how to solve it? Well, block coordinate descent. Fix one of the variable, solve the subproblem, and then fix the another variable, solve the subproblem, and repeat. The subproblem on H is very simple. If you look carefully here, this is the subproblem on H, basically just a non-negatively square. So it's relatively simple to solve. The main difficulty of NUMF is on solving W. And since we have constraint on columns of W, so we cannot solve this problem matrix-wise. We have to solve it column-wise. So here is an illustration expressing this objective function as a function of Wi. You can pause to look at it carefully. So now a subproblem on one column of W is a LCQP. And this problem is convex because here we know the P. However, in general, we don't know the P. Therefore, star is a non-convex problem. So how to solve this problem? We use a very naive approach. Brute force. Try all the P on star. Pick the best one as the solution for star. You may wonder, can we solve star directly? Yes, theoretically you can, but very expensive, so we don't do that. So let me summarize where we are. We want to solve the NUMF problem by BCD. Then the bottleneck of the BCD is the subproblem of W. We have the star and the star problem. And we are using brute force on all the P for the star and pick the best P for the star star. And since we are doing brute force, so brute force is okay if the search space of P, that is on all the integer in M, is small. However, in general, M can be very large. That is, the dimension of the W can be very large. So brute force is not okay. So we need speed up. We first solve star by accelerated projected gradient, that is, accelerated first order method. There's no luxuries for using second order method because we are already running a brute force here. The second speed up is doing something called dimension reduction. Well, brute forcing on P is to search all the integer here. We make this search space small, then brute force is okay. So what dimension reduction we use? Multigrid. Why? Because multigrid preserve NU. Other techniques, for example, PCA, Gaussian sampling, these are also dimension reduction method, but they don't work here because they destroy NU. So now I will go very fast on accelerated projected gradient on solving star. You solve it by projected gradient, so you need to project, and this red part is very hard to project. So we do a variable transform. This variable is u times w, so we let it y. And transform it, this star problem can be expressed in this form, which in simplified term is this problem, star prime. We solve star prime, then we get y star. This solution can be transferred back to a w star by this relation. That is, we solve this problem, then we get the solution of this problem. Then how to solve star prime? Again, APG. The difference between the star prime and the star is that now here, this inequality constraint, we only have one variable. Before, we have a matrix multiplied, but now we don't have that matrix. This suddenly becomes easier to solve. We solve it by projected gradient, so we need to do the projection step to project to this set. We do it by partial Lagrangian. We add the equality constraint here and keep the inequality constraint here. This min-max will give us the solution y star because strong duality hold. And this closed form is a soft thresholding operator. We only need to find this new star, which is the Lagrangian multiplier, which is the root of this equation. Now move to the dimension reduction, that is the multigrid. The idea is very simple. Instead of working on W, a long vector, we work on a restricted version. That is, we multiply matrix R, make this vector shorter. So R looks like this. And why doing multigrid? Well, because this R preserves NU. The whole theorem here, the proof is just 3 sentences. You can read the paper for the proof. So what's exactly the 3 sentence proof? The goal here is to show that Rx is NU if X is NU. First, this R can always be decomposed into a sum of 3 matrices A, B, C, where A is the matrix having only the A, and B having only the B on top, and C is taking only the B on the bottom. So Rx equal to Ax plus Bx plus Cx. Ax, Bx, Cx are NU because, look closely, A subsample the odd entry of vector x multiplied by A, and BC subsampling the even entries of vector x and multiply them by constant b. So Ax, Bx, Cx are subvectors of NU vectors, which are NU. The last sentence is very simple. Because of the sentence 2, we know that Ax, Bx, Cx are all NU vectors. So we just need to show that their sum is NU. What we need is to check their p-value. By making use of the NU characterization, we know that two NU vectors, their sum is NU if their p are consecutive integers. Ax plus Bx plus Cx is NU because their p are differ at most 1. So this is the 3 sentence proof. In the paper, of course, there are more than 3 sentences, but those are just to make sure the mathematics is correct. This 3 sentence is the core idea of the proof. So now this is the whole algorithm. Very simple. You first compress the data by doing restriction, then you solve the coarse problem using brute force. Because this is a smaller sized problem, so brute force is okay. Then you interpolate the solution on the coarse level back to the original problem, and now you have this P0, so you don't need to do brute force on the original file level. In this case, solving this will be very fast. What about convergence? Well, the problem is non-convex and block non-convex. So the best you can get from optimization theory is that the sequence, the variable WH, will converge to a local minima. If you want global convergence, you need something outside optimization. That is, we want to answer the question, when does solving NUMF give a unique solution? That is the global minima. There are 3 identifiability results in the paper. You can read it for details. The general idea is that it depends on the support of the vector. For these 2 vectors, their support does not overlap. In this case, solving NUMF with this kind of vector will give you unique solution. Lastly, these are the numerics. First of all, this is a toy problem for illustrating the multigrid will give you faster convergence. The black curve is the convergence in time for the fitting norm with no grid. That is just a normal algorithm. The blue and the green are with 1-layer and 2-layer multigrid. You can see that multigrid saves a lot of time. And this is also the case for fitting the ground truth. Note that NUMF is a non-convex problem, but here, this curve showing that the W actually is converging to the global minimum. It's because this problem satisfies the identifiability assumption. I mean, the W here is tailor-made such that the assumptions in those theories are satisfied, and therefore, they converge to the global minimum. And we can also see that Multigrid is doing a good job. Here is a slide showing the application of NUMF. Here are the dataset from Belgian BA chromatography data, and you can see that they are NU. This is actually the motivation of NUMF. And then we decompose it into 6 bases. You can see that only NUMF is giving you meaningful decomposition, because for the NMF and separable NMF, they give you highly mixed solution. And for these NUMF solutions, you can just go to the data book and check match with the peak, and then you will know, oh, what is this kind of chemical in the BA. This slide is showing a special ability of NUMF, that is, the rank can be larger than the size of the data. Here you are factorizing a vector into 8 vector. This is not possible for NMF. And furthermore, the first 3 peaks of this data satisfy the assumption of the identifiability, and therefore they will be perfectly recovered. But for the other part, not perfectly recovered because their support overlap. The identifiability of overlapped vector is actually still an open problem. So lastly, this is summary. I talk about NUMF, the problem, the categorization, the algorithm, and slightly talk about the identifiability and application. That's all. Have a nice day.